We ran a few containers in the last chapter, but we didn't really talk in detail about what was happening. Our Hello O'Reilly container ran the command echo hello O'Reilly, and our Hello O'Reilly HTTP container ran the Ruby command. Containers exist to wrap a single process. And while it's possible to treat a container like a full virtual machine and running multiple processes inside, a container's lifecycle is directly tied to the process running as PID1 within. The command that runs inside a container can either be specified by the Docker image itself or by the user running the container. Let's start with a simple example of a container where we specify the command when we run it. We'll use the Ubuntu Docker image. Most Linux distributions provide a Docker image for each version of their operating system. When we run a container, we always need to specify an image to use. The image name comes after Docker run, and will always follow any flags that we might pass in. Since we want to use the latest version of Ubuntu, we'll just type Ubuntu. The Ubuntu image doesn't specify a useful command. It's up to us to provide a command to run within the container. Let's simply print the working directory using the pwd command. Notice that when we run a container and we don't have the image locally, it'll automatically download it from Docker Hub. So we don't have the Ubuntu image on our machine, and so we're downloading it. It's not very exciting output, but it worked. What happened is we created an Ubuntu container to run the pwd command. Let's try running pwd on our local host machine. Notice that the output is completely different. That's because our container has its own isolated view of the operating environment. Running pwd shows that the container has its own file system, but it also has its own user ID space, process trees, and networking. Running an instantaneous short-lived command like pwd in a container means that our container will only exist for a split second while the process is running. This can be useful for lots of tasks that typically require a specific setup or environment. So how can we investigate the inside of a container without running single commands? Docker offers the -i flag, which allows you to run a container in interactive mode. The I flag can be used in conjunction with the T flag to assign a terminal to the container. Using these parameters and specifying bin bash as the container command allows us to run commands from within the container. We're in. Notice my prompt has changed. It now says root at some UUID string. We're now running inside the container as root, and the UUID is the hostname of the container. Let's verify. That checks out. Each Docker container is assigned a unique hash as a container ID. This ID is also the hostname inside the container. Let's run ls and see our isolated view of the file system. We're at the file system root, and as you can see, most of the basic Linux directories are here. So let's run ps and see what processes are running. There's only two processes running within our container, bash and the ps that we ran. Bash is PID1, which means that the container's existence is bound to the bash shell that we're currently running. We can end our shell session by running the command exit. This will end our bash session and thereby exit the container. Now we're back on our host machine. Let's see if our Docker container is still running using the docker ps command. Docker ps is similar to the Linux and Unix ps, only it shows running containers instead of processes. No Docker containers are listed. That's because our container finished with its process. In the next lesson, we'll cover the different Docker features for running containers.